Well, good evening, everyone, and welcome to this Department of Earth Sciences Alumni online seminar event. My name is Richard Harrison. I'm the head of department. It's my pleasure to welcome you all this evening. We've got two fantastic speakers tonight, Marian Holness and Nick Tosca. Nigel will introduce them in a second. Just to remind you that the talks are being recorded, so you're aware of that. You'll have a chance to ask questions in the Q&A after each of the talks. And what we hope to do, a new innovation for tonight's online event, is that after the talks are finished, there'll be a social event online in Gathertown, and we'll give you the details of how that runs afterwards. But we're looking forward to that because it gives you a chance to talk to the speakers more informally after the event, or talk to each other and find your friends. So we'll see how that goes, and we'd like to get your feedback on whether you think that's a good innovation or not. We've got a program of live events, in-person events planned also coming up later on next year in March and in May. So look out for details of those. But for now, I'll hand over to Nigel Woodcock, who will introduce tonight's two speakers to you.
Thanks, Rich. So first up, we've got Marian Holness. Marian was an undergraduate and a postgraduate in Cambridge in the 80s. Then she went off to Edinburgh to do postdocs, and she arrived back in Cambridge in 1997. Since then, significantly, she's been promoted to the first female Earth Sciences professor in Cambridge. So she's also a fellow of Trinity. She works on really textures in high temperature rocks, how melting occurs and how solidification occurs. She started off on the dark side in working on gabbros and such like, but she's seen the light, as it were, and works more and more on granites. And she's going to talk about this sort of thing, particularly with respect to thin sections, which I should say she's renowned for in a teaching sense. She has some wonderful teaching videos on the sort of dark art of interpreting thin sections, which we still do a lot of in Cambridge. You'll be glad to hear. So over to Marian.
Thanks very much, Nigel. That's a very nice introduction. I should add, actually, in the context of promotion to professor, it took 281 years from the first professor of Earth Sciences in Cambridge till I got my chair. It's quite a long time. Right, so what I'm going to do is share my screen. I'll get this to work. Right, and I'm going to share my slides, if I can do that. Okay, is that all working? Right, so I'm going to be talking about the fine art of working out the fluid dynamics that were happening while magma was solidifying from completely solidified bodies. So, oh, this is not, oh yeah, it's working now, sorry. Okay, so what's a magma chamber? Where does magma sit in the crust? Well, on the left here, you can see this is just grabbed from Wikipedia. You've got a batch of magma sort of frozen, it's sitting in the crust, it's just sort of stuck in the crust, and it will start to cool because it's losing heat to its surroundings. And it's what happens in that magma chamber that actually affects the physical behavior of the magma that gets erupted at the top. So there's one end member belief that is sort of like a balloon and straw model, where we've got a big vat of magma that's just sitting there and doing its thing in the crust, sort of liquid rich body. But more recently, there's been a move towards thinking of magma being stored in the crust as a very, very complicated series of interconnected batches, a sort of transcrustal magma feeder zone that feeds the volcanoes up at the surface, in which case it's much more complicated, and the actual volume of free liquid that you have in any one place in this transcrustal system might be actually very small in contrast to the older version of what's going on. So what happens in the magma chamber actually really affects what magma we get up at the surface. So this is some basalt, and you can see it's actually pretty runny. I mean, basalt erupting from the mantle has got a viscosity very similar to that of high quality tomato ketchup. And so the sorts of volcanic eruptions that we get tend to be not terribly explosive, because the gas that that creates the explosions can get out very, very easily. So this is pretty much as explosive as it gets. This is some fire fountains from in Iceland. Whereas if magma is allowed to sit in its chamber for a long time and fractionate, what you end up with is a much more silica-rich magma, which is extraordinarily sticky. And so you don't tend to get those lava flows like this. You get something, this is Mount St. Helens in 2006, where it's creating a dome of andesite lava. Andesite can't flow in the way that a basalt can. So this is a time-lapse photography. You can see it sort of churning up and making a dome. It's very, very, very different. And part of the problem with really sticky magmas is that you exsolve gas when you depressurize it. And if the gas can't escape, eventually you're going to trigger an absolutely massive explosive eruption. And this image here is of the Mount St. Helens eruption in 1980 in northwestern United States. So what happens in the magma chamber, how much you can fractionate it, how will control its physical behavior. Is it just going to come out really easily and there'll be no loss of life? You can just outrun the lava, it's all fine? Or are you going to get an absolutely massive climate changing eruption like this one here? So we really care about this. So that the whole business of fractionation is created when you can separate the crystals that are forming from the residual liquid. And whether or not the magma in the chamber can convect will really affect how easy it is to separate these crystals out and to drive fractionation. So this question, convection, is really, really important in understanding magma chamber dynamics. We need to be able to interrogate now solidified intrusions and say, did this magma convect while it was solidifying? And I'm going to tell you some ways of how we can do that with fully solidified rocks. So the first place we're going to go is the east coast of Greenland. This is a nice little cartoon here showing what the east coast of Greenland looks like. So there's this ancient bit of continental crust here. The hotspot that's now underneath Iceland triggered an enormous amount of eruption of basaltic magma. And that's what these things are. These are sort of plateau lavas. And at the boundary, this buoyancy sort of level of neutral buoyancy, we got some of those magmas, which were supposed to be plateau lavas, trapped at that unconformity and formed an intrusion. And the Skaregard is one of those. So it's basaltic magma, got trapped about a couple of kilometers below the surface at the unconformity between the Precambrian gneisses, the sort of continental crust, and the overlying plateau lavas. And it formed a sort of pocket, a space that was bounded by normal faults in the extending margin of the East Greenland bit of continental crust. It's about 10 kilometers across and about 4 kilometers deep. And there's a geological map of it here. So there's a big glacier going down here. This is the sea. And because it's pretty, what's the word, barren there, the exposure is absolutely brilliant. So the only bits you can't actually map are the very, very steep bits and the bits that are covered in ice. And there is our outline here. And it's essentially is a vat of magma stuck there in the crust, and it's losing heat from top wall, for the top the floor and the sides, and it's crystallizing inwards. So this is a nice little cartoon here. There's the roof, the walls, and the floor, and we've got progressive fractionation in. So the floor series is mirrored at the roof and at the walls, and it all just met here at the sandwich horizon. This is SH, the sandwich horizon. That's the last bit of liquid to actually solidify. So it's a really iconic intrusion, partly because it's so fantastically well exposed, and partly because it's very unusual in that it was totally undisrupted by more magma coming in or eruptions. So it was a closed system. It's like a perfect laboratory experiment of what happens when you put a large batch of basaltic magma in the crust. So this is a lovely cartoon that Neil Irvine drew, which essentially summarizes the processes that were happening in the Skaergård. So here you can see at the top, there's the unconformity where it got stuck, the magma got stuck. Here is our gneiss, got these steep walls, vertical walls that are actually normal faults, extensional faults. And you can see it's crystallizing in from the floor, up from the roof, in from the walls. And he's drawn all these convection cells in here. This magma was crystal poor in the center, and it was furiously convecting away. And we had material dropping down from the roof and forming these blocks here. And we had crystal-rich currents falling off the walls. Now, the reason he could draw this diagram, this concept of what was going on in the magma chamber, is because of what the rocks look like. So if we go near the bottom of the intrusion, what you can see, this is a gabbro, and the paler bits here are rich in plagioclase, and the darker bits are rich in things like olivine, clinopyroxene, and oxides. And you can see there's layering. But the layering is not simple. It looks actually like a sand dune. And in fact, when this was first discovered by Lawrence Wager in 1933, he thought it was sedimentary rocks when he was looking at it from a ship, because that's what it looks like. But it's actually like an igneous sediment. So it looks like a sand dune with these cross sets that are being truncated here. So you've got this early set of bedding, and then it's truncated, and then another set of bedding comes in here. It's a really, really dynamic environment. And I should add that just here, this is a rifle for scale. And then the reason that we need rifles is because not all the apex predators in East Greenland are quite as cuddly as these ones look here. So you always need to have a gun with you. It focuses the mind, I can tell you. So yes, we get these sediments, magmatic sediments, if you like, looking like sand dunes, but we also get features like this. This is a glacially polished surface, and you can see these bands running across it. So they've all been tilted. So the dip on this is about 20, 30 degrees because of the extension of that margin of Greenland. So they've been stretched. But you can see this, the gabbro here is completely homogeneous and uniform. And over here it is as well. But then we get these layers that are less than a meter thick that are very strongly modally graded. So you've got very dark bases, and they grade up to form very, very white tops. So here we've got low density plagioclase, and then the high density minerals are all here at the bottom. So it's modally graded in terms of the mineralogy, but this is actually density sorting. So what we're looking at is an environment where a lot of the time crystals are just settling onto the floor or nucleating and growing in situ on the floor and making this sort of homogeneous stuff. But every so often we have a catastrophic event that dumps out these a plume, a rich sort of liquid plume that's rich in crystals. And as it flows across the floor, you get density sorting. So all the dense minerals get dropped out first, and then the lighter ones get suspended for longer. Now, this is really, really similar to the sorts of things that you see in sedimentary rocks. This is like a turbidity current, and it's a particle-rich flow that's running down a slope. And as it comes to rest, it will develop this density graded, grain size graded layer. So that's what we're seeing in the Skaergård. So these plumes are pouring down the walls like this. They're crystal rich. This is all part of the convective system. And as they roll out down the floor like this, they look exactly like this thing here, and they create one of those little layers. We also see evidence that some of these crystal-rich plumes that are coming down the walls can come down with such force that they actually erode channels for themselves. So if we just zoom in on this, you can see there are nice layers here, nice planar layers, but every so often you get an erosive event, like a river channel. We've created a river channel, and within the channel, that crystal-rich plume has dumped out a density sorted graded modal layer. There's another one there. Okay, so we've got two in this image. But in some places in the intrusion, we find that the currents are always coming down the same place in the walls, and they're always rolling out on the floor in the same place. And you get these stacked channels, if you like, where every one of these is a single catastrophic collapse event. And if we're just zooming in closer here, you can see there's a collapse event there, making a graded layer. Then there's another one. The bases are always rich in the dense minerals. And you can see that the exact position of the channel is changing by, up to 5 meters sometimes, but it's always roughly in the same place. So we've got these plumes pouring off down the walls, always in the same place in the walls, which is kind of interesting. If we look closely in these channels, we can see that there are fabrics. So here, these are elongate plagioclase grains that show up nicely because it was wet, and they're all randomly aligned. That's outside the channels, but inside the channels, there's a single depositional event. There's another single depositional event. Can you see that the plagioclases here are now elongated? They're aligned. I mean, the elongate plagioclases have got a preferred alignment parallel to the current. So this current's bringing them down and sorting them out so that they're all pointing in the direction of the flow. So the basic idea is that what we had is these trough bands, they're called. We've got these troughs, these channels, the crystal-rich plumes, part of the convective system, are pouring down the walls and coming down these channels and dropping off their crystal load as they do so. And all the elongate grains end up pointing parallel to the axis of the trough. And when we look at them in thin section, look at these rocks in thin section, they essentially look like sedimentary rocks. What we've got is these beautiful little plagioclase grains here. They're nice euhedral grains. They've grown somewhere else up on the walls, and they've just been dropped down in these channels, just like grains of sand in a sedimentary rock. It's really very interesting. There's a nice element map here where you can see the plagioclase crystals here, and this black stuff in the middle is like a quartz cement. So it's almost directly analogous to a sandstone, except the clasts here are plagioclase grains. And yeah, I think in terms of, this is sedimentary petrology in a magma chamber. So we've got one of these stacked layers here, and this is our location of samples. And you can start doing funky things, working out the preferred alignment of crystals. And you can end up with these plots here that show you, yes, you've got a very, very strong fabric. All the 100 axes of the plagioclase crystals are all pointing in one direction. So we've got a really beautiful, strong fabric that's created by these density currents. So on Skaregard, with field evidence, we've got abundant evidence for sedimentation. It's a sedimentary environment in an igneous setting. And we've got reworking of the crystal mush, got these magmatic currents, very, very dynamic environment. So it's clearly convecting, and the convection is driven by cooling from the walls and the roof. But Skaregard is fine, it's kilometre scale. What can we infer about convection in smaller bodies, sort of 100 meters? They don't tend to have the kind of layering that we can interpret in Skaregard quite so easily. So what else can we do? Well, I've been spending some time worrying about sills, basaltic sills. These are sort of roughly horizontal tabular intrusions, and these are some in Antarctica. They can be several hundreds of meters thick, really, really big. But what I'm going to tell you about is in Scotland. So it forms the Sheehan tiles. So the Sheehans are here. This is Skye. This is the mainland of Scotland. And this is standing on the Isle of Lewis and looking out. There's the mainland of Scotland, and there are the Sheehans there. Now the Sheehans are essentially made of two enormous sills. So this is a view from the sea. You can see those beautiful columnar joints. This is essentially a dolerite sill. And the magma forming these sills carried a crystal load, a crystal cargo of olivine. So this is just a generic photograph. This isn't from the shear, and this is just from Wikipedia. Look at these beautiful olivine crystals, just to remind you what olivine looks like. So the sills and the shears were composite. So the one I'm going to tell you about was actually formed of 4 separate intrusions, each one bringing in varying amounts of olivine cargo. But a lot of it, a lot of the sill is actually this major intrusive body here. And there's all the olivine cargo settled at the floor. So this is a nice stratigraphic column. So we're looking at this part of the sill here. And this is the amount of olivine that we see in the sill coming up here. So it's very high at the bottom, and then it decreases. If we look at the chill zone, the bottom of it here, you can see the olivine crystals. Here they are. This is the cargo, and this is a rapidly crystallized magma. So what you can do is just look sequentially up through this accumulation of olivine on the base. So we're looking down here, and I've just drawn round them, so they're very, very easy to see. They're nice, round, sort of forming clusters with a few grains. As we go up, they're starting to get smaller. We've got a fining upward sequence of this dropped cargo. As we go up still, do you notice that we've dropped our olivine quite rapidly, and then the amount of decrease starts slowing. We've got a real break in slope here. And coinciding with that break in slope is the onset of clusters, the arrival of clusters olivine. And here's just what they look like in thin sections. So they've been clustered like this. They're nice equant grains. They can't have formed their clusters on the floor. The only way to form these clusters is if these olivine grains are being suspended in magma, so they can come together and stick together and then carry on grow. So they formed before deposition. And we're going higher up, and those clusters are getting bigger, and they're bigger still, and more grains. And we've also got evidence of growth of olivines on their edges after they'd formed the clusters. Now, if we go up to the roof now, up here, the clusters are there again. There's very little olivine here, but suddenly the clusters arrive, and they're absolutely massive. And we go up again, and now they're going fine again. So we've got a mirroring at the roof of what we've got at the floor. So just to summarize what we're seeing at the floor, we have got a fining upward sequence and then a coarsening upward sequence. Now this is really interesting because if these large clusters were present in the cargo, they wouldn't be at the top here, they'd be at the bottom. We would have a nice simple fining upward sequence, but we don't have that. We've got coarsening upwards. So we cannot have had these things present in the original cargo. They must have grown after emplacement. So we can think about how we actually make this happen by just putting some numbers in, having some sort of timescales for growth and for settling. So how long would a sill like this take to solidify? Well, we could just use the characteristic timescale for the cooling, the sort of thermal half-life, if you like. And we're talking decades. It's going to take decades to change the temperature of a sill this thick, 140 meters. And the time to fully solidify is of the order of a century. So that's the sort of time scales we're dealing with. Now let's consider the fact that we've got these big olivine grains at the top of the sill. If these were in a static magma, okay, these big things here are going to sink down because they're dense. And we can calculate the approximate velocity at which they'll sink by just using the Stokes settling velocity. So we can plug in some numbers. The viscosity of magma, basaltic magma, is about 1 to 100 Pascal seconds. Now, if they were in a static magma and they were up near the roof and they're going to settle down, in order to be trapped at the roof, the solidification front must come down and gollop them up and freeze them in there. So how quickly does it take to solidify downwards to where we're seeing them? They're 10 meters below the top of the sill. Well, the time scale for solidification of the sill to this point is given by d squared, where that's 10 meters, and that is the thermal conductivity, which is 10 to the minus 6 meters squared per second. Whoops. And in order to trap these large crystals 10 meters above, 10 meters below the roof, the viscosity would have to be up to 1,000 times greater than it actually is. It cannot work. So the only way we could have got those olivines up where they are, as if they were brought up to the roof in a convection current. Okay, it cannot have been a static magma. It must have been convecting. We can do something similar here at the bottom. We can also say, right, okay, settling timescales, that's Stokes settling, but we've got crystals all the way up here. We've got 50 meters of olivine crystals. They would settle down way too fast if it were a static magma. But if we have the magma convecting, the convecting magma can keep crystals in suspension for a long time, and they will only escape the convecting flow once they enter the static boundary layer at the bottom of the convection cell. And the half-life for keeping the crystals in suspension was worked out ages ago. It's just given by the natural log of 2h, where h is the thickness of the sill, over the Stokes settling velocity. We know what the Stokes settling velocity is, we can put that in. So the half-life for crystal retention, the time it takes to lose half your crystals, can be up to 2 years, depending on exactly which viscosity we have. So actually we would have settled out all of our olivine, well, 94% of our olivine in about 5 half-lives, which can be about 10 years, which is on the nail for the kind of timescales we have for cooling of this body. Remember, the characteristic timescale for cooling of this is of the order a couple of decades. So that's how it works. That's how we get those big olivines up at the top. And that's how we get the olivines scattered through 50 meters of the base of this. It was convecting. This is the signature of convection. So the story for the Shiant is that most of the olivine cargo was dropped very, very early on to make the finding upward sequence, just as you would in a sediment. But some of those crystals could not settle out because they were too teeny weeny. So they were just kept up, sort of unsettled in the main body of the magma. I should say also, yes, that we get very, very little olivine right up at the roof, simply because most of it settled to the floor. But then once most of the cargo had dropped out, the magma started to convect. And those tiny olivine grains that from the cargo that didn't settle started to grow. And they grew bigger and bigger. And the longer they were kept in suspension, the bigger they could grow. So as we go up here, we see crystals that were retained longer in the convecting magma, so they're bigger. That is how you get the coarsening upwards. And then at the roof, you get the coarsening inwards because the crystals that we see lower and lower and lower have been kept suspended for longer and longer. And they're brought up by convection currents and then just trapped at the roof once they get entangled with the crystals growing downwards from the roof. So at this point here, in this middle point, there's no more olivine left. All the olivine cargo, all the main crystals have all just dropped to the floor or what's stuck to the roof. So all the olivine, these very, very small amounts of olivine here, this is all now just growing in a crystal lush. So just to conclude, if you're lucky enough to have a really large body, you can look for outcrop scale evidence of gravity sorting, which is telling you that you've got crystal rich plumes falling off the roof, running down the walls. This is evidence of convection. We've got really lovely evidence in Skaergård for erosion by currents and redeposition. So this is clearly a sedimentary environment. This is dynamic, convective. On the grain scale, look for fabrics. Crystal alignment, grain alignment happens because you've got convective currents moving the crystals around. And then if we don't have the advantage of all this beautiful layering that we have in Skaergård, any evidence from settled crystal loads can also tell you about convection. Upwards coarsening is proof positive that we had convection in the system. Okay, oh yes, and I should also say the spatial distribution tells us about delays in settling. If you've got cargo that's still sort of being preserved meters and meters off the floor, you know it was kept from settling by convection. Okay, so that's me done.
Thanks very much, Marion. That was wonderful. I'm not the only one to have been impressed and inspired by those graded beds and the channels and the various sedimentary features. We've got a couple of questions straight away on that sort of thing. So Tim's asking, he says the sedimentary events that lead to the graded beds are relatively short-lived, perhaps measured in hours, or he's talking about in sedimentary rocks. Is there any indication of how long the igneous events lasted?
So, got a cat.
Oh, right.
Well, I think they're equivalently very short events, but of course the viscosity of the system and the Reynolds number that we're dealing with, all these dimensionless numbers are much, much higher. So things would be slower, but we might be talking days or maybe a week, just depending on how quickly it can run down. So yeah, it's a similarly very short catastrophic event.
Okay. And related to that, closely related, Stuart's asking, is there dating data that provides frequency information for the channeling events? I suppose how frequently each flow came down, the time between the events rather than the time of the events, I guess.
I would love to know that. I really would. I mean, the stuff I'm working on in Skaregard shows at the moment that there was episodic catastrophic collapse of the walls, of a crystal mush on the walls. You can see it on the floor. You can see it because there's hiatuses in the sequences of the walls. And those were triggered by faulting. Remember, this was intruded in an actively stretching continental margin as the North Atlantic was opening. So there was continual earthquakes. So I'm wondering if some of these things, I mean, I can see the major earthquakes being recorded in collapse, but I'm wondering whether some of these really small ones might also have been jiggled around by some sort of micro seismicity. It'd be really, really interesting to be able to put timescales on it.
Okay. And here's an interesting question from Daniel, who won't be anonymous to you probably. He says, thank you for quoting my research from ages ago. Can I ask how common magma chambers are thought to be these days? Is there geophysical evidence for them, for example?
Yeah, this is a really interesting question. So there's this huge push amongst certain members of the igneous community to say that magma chambers don't exist, that it's impossible to have them exist. Because we don't see evidence for them now, because geophysically we do not have any evidence that anywhere on the planet at the moment there is a large vat of crystal poor magma. But that's now, we've only been doing these seismic things for, I don't know, a century at the very most. And it's just not long enough time. I think if we waited 1 million years, we might see another one, because there aren't actually that many. I mean, I think Rum and Skaregard certainly, Bushveld certainly, these were definitely crystal poor vats of magma for a significant period of time. But through geological history, I mean, the Bushveld's 2 billion years old, Skaregard's 60 million years old. If we waited long enough, we would definitely see one, because they definitely did exist. But I'm absolutely happy with the fact that there aren't any right now. But, if we wait long enough, one will fall.
Good, thanks, Marion. I think time's pushing on. That's the end of the questions in the Q&A for now. There'll be more chance, of course, if people think of questions, to come to the Gathertown event at the end and ask Marion in person, as it were. For now, let's move on to the second presentation of the evening, which is by Nick Tosca. Nick was a student in the States. He first at Albany and then at Stony Brook. Then he was a postdoc first at Harvard, and then for reasons I've never asked him, he moved over decided to move over to Britain. He got a JRF, a junior research fellowship at Churchill. That's when we first got to know him in Cambridge for 2 or 3 years. And then it's as though he decided to collect jobs at all the oldest 3 universities in Britain, and so he went off to St Andrews on a lectureship for 3 years, and then to Oxford on an assistant professorship for about 6 years, and only last year we attracted him back to Cambridge as Professor of Mineralogy and Petrology. He does, though, if you like, soft rock mineralogy and petrology. He's an aqueous geochemist, I suppose, and does chemical sedimentology. For some time, he's been increasingly involved in exploration of the sedimentary rocks on Mars, and that's what he's going to talk to us about tonight. Over to you, Nick.
Thank you, Nigel. It is a real pleasure to speak at this event and to share some exciting results from the Mars 2020 mission with you all. Okay, so many of you might be familiar with the Mars 2020 Perseverance Rover, partly because its dramatically successful landing sort of shocked and surprised the world a few months ago because it was videoed in exquisite detail. One reason why this mission differs straight away from previous missions is because NASA engineers decided that they could fit a number of high-resolution cameras onto the rover and actually capture in dramatic detail the landing of the rover to its final resting place at Jezero Crater. The videos from that landing sequence were distributed far and wide, and I never get tired of seeing it. So what I'm going to do is start off with the last minute. This is real footage.
Completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
So as the spacecraft is hurtling towards the
surface. We started our
surface.
constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So as I said, this mission captured the interest and imagination of most of the public. And since then, it's gathered a large following. And so what I'm going to talk about today are really the scientific goals of the mission, how that fits into the broader, our general knowledge of Mars as a planet, and what that can tell us about the tantalizing problem of the origins of life. So as you may know, Perseverance is looking for signs of ancient life on Mars. And one amazing thing about this mission is that it also kickstarts a decade-long effort in Mars sample return. So the samples that are being collected by the Perseverance rover, we hope, and we're reasonably certain, given that most of these missions are in development, is that those samples will be returned to Earth within about 10 years or so. And that's a very exciting development. Of course, the big question to ask is why, and why bother? Searching for signs of ancient life could potentially be the longest of long shots. And so this is a question that's important to ask straight away. And it's important to sort of go through some of the reasons that I think adequately answer this question. So I think the why are we doing this starts with some recent developments in the field of prebiotic chemistry, which is chemistry or chemical reactions that we believe paved the way that ultimately facilitated the development of cellular life on Earth. Over the last few years, there have been some very exciting, dramatic developments in this field, led in large part by John Sutherland, an organic chemist who's actually based at the Laboratory for Molecular Biology here in Cambridge. And to summarize those results, those groups have discovered new ways in which life's building blocks could have been formed spontaneously from rather simple molecules that are likely to have been supplied by ancient environments. So specifically hydrogen cyanide, sulfite, and phosphate are key players in this chemistry. And they've documented that with those simple feedstock molecules, with one multi-component reaction network, you can actually generate most of the building blocks, the key building blocks that are required for life. So that includes lipid molecules, which often come together in bilayers, which this animation is showing here, which can form protovesicles, which eventually become cellular membranes. But that also includes nucleotides, the building blocks which eventually carry information encoded in RNA. and then also precursors to amino acids. Now, these are really astounding results, and really mark a major success in this field, because it had stagnated for decades. Understanding and facilitating this chemistry it really sort of kind of stopped for decades until some of these recent breakthroughs. But the questions that we ask as geologists are, what sorts of environments might have made this chemistry possible? And perhaps even more exciting to someone like me is that there are specific environmental requirements that organic chemists like John Sutherland have actually outlined that give us a sense of environments that could actually facilitate some of this prebiotic chemistry. And those requirements for at least some viable pathways are illustrated in this schematic. And so in panel A, they believe that most of the feedstock molecules need to be concentrated in a lake that eventually can be evaporated, which is good for concentrating feedstock molecules, but also drives pH fluctuations that can facilitate important chemical reactions. And so that leads to ultimate evaporation or drying, as you can see in panel B. Now, part of that salt mineral assemblage, they argue, should be ferrocyanide salts. So ferrocyanide is simply a aqueous complex between ferrous iron and cyanide. It's quite strong, and it can crystallize in solid form in the form of ferrocyanide salts. But these are important precursors, because if those ferrocyanide salts are heated up, as suggested in panel B, either by contact metamorphism, which could have been driven by impacts, for example, or igneous intrusions, then those ferrocyanides actually transform to incredibly useful products like cyanamide, which can then very easily be transformed into the building blocks that I just talked about. But of course, that involves re-wetting those salts to take advantage of the newly liberated compounds in panel D. Now, this is really exciting because it offers very detailed environmental requirements for how this specific pathway might operate, and it actually gives us a sense of the types of environments that could facilitate that. It sort of gives us a sense of the recipe, if you like, for kickstarting what we'd call prebiotic chemistry. Of course, it's a very long leap from developing the chemical building blocks to life to then developing a self-replicating cellular system. But this gives a good sense of the major revolutions in this field, and they're most exciting now because they give us a strong connection to environments and geology. Of course, there's a big problem because as geologists, if we want to understand the environments that could have facilitated or hosted the origins of life, we have to reach pretty far back in time. So that's illustrated in this timeline here. The red box includes just a very rough estimate of when we think life might have gotten started on Earth. And that is sort of positioned between some key geochemical evidence for the operation of biologically driven carbon and sulfur cycles. And then, of course, the first appearance of liquid water and the end of some of the last major potentially sterilizing impacts. So first off, that's a big swath of time, but second of all, it was a long, long time ago. And as geologists, we probably know that we have very limited access to sedimentary rocks that actually archive that time period and those environments. This just gives an example of the problem we're up against. So this is a compilation of statistics that tell us about the total number of sedimentary packages deposited on Laurentia or in North America through geologic time. And this is compiled by an effort called MacroStrat by Shannon Peters in 2018. As you can see here, as you go further back in time, the number of sedimentary packages we have that potentially record that time interval decreases substantially. Of course, in Laurentia's case, a big part of this had to do with Neoproterozoic glaciation, which was responsible for forming the what's called the Great Unconformity close to the Precambrian-Cambrian boundary. But nevertheless, this general trend has been observed on cratons across the world for one simple reason. And that reason is obvious if we look at a geological map of the Earth, and that reason is plate tectonics. Our planet benefits from a process that in some cases can efficiently recycle crustal materials, but in other cases significantly modifies crustal materials. And so ancient sedimentary rocks tend to be poorly preserved because they're subject to the dynamic processes that are associated with modification of our crust. So this means that if we want to go back in time and understand the environments that could facilitate prebiotic chemistry and the origins of life, we're in trouble because we don't have very many well-preserved sedimentary successions that could tell us about those environments. And that's where Mars comes in. Mars preserves a record of ancient environments that we think exists nowhere else in the solar system. And this diagram should convince you why that's the case. So the diagram illustrates rocks that are between the ages of about 3.5 to over 4 billion years old. Now the relative ages can be estimated with some certainty. The absolute ages depend on a method called crater counting statistics that takes advantage of the statistical decrease in bombardment history that's been compiled from data on the moon and some other rocky planets. But regardless of the error associated with that, you can't get away from the conclusion that there's a significant portion of the Martian geological record that is older than we could ever get our hands on the Earth. And so what makes this even more exciting is that we've learned over the last few years that geological record includes exquisitely preserved sedimentary rocks. And so I've got just a few examples of the images of these sedimentary successions that are taken with high resolution orbiting missions to Mars. And you can see the exquisite detail preserved here and the scale that's on these images. It's really striking. And I guess we've realized over the last decade or so that this sedimentary record is extensive and it archives a rich environmental history that happened early in Mars's planetary development. And so that's holding crucial information about planetary environments and their capacity to host life, and could teach us an awful lot about what might have happened on the Earth during a similar time interval. So what is that history? What is it that we know about the geological history of Mars? This is a very broad summary figure that sort of pieces together some major planetary events through Mars's history and compares the geological history on Mars to the geological timeline on Earth, just to give you a sense for the intervals in time that we're talking with here. So we know that early on in its history, Mars was dominated by volcanism, in particular the emplacement of some very large volcanic provinces. And it was also subject to some major impactor events, some very, very large basin forming impacts and a significant flux of smaller impactors between about 3.5 and 4 billion years ago. But overlaying on top of those major events, there's extensive evidence for liquid water, both in the form of surface geology and surface geomorphology, so in the form of valley networks and outflow channels and very large regions across the surface that have been modified by a subaqueous deposition. And then, of course, there's mineralogical evidence. So we have years and years of orbital vibrational spectroscopy that gives us a sense for how minerals are distributed within the surface geology. And so there are significant amounts of iron and magnesium phyllosilicates or clays, sulfate minerals, evaporite minerals. So really a rich sort of mineralogical tapestry, if you like, of processes that involve liquid water. But most of that is confined to very early on in Mars's history, before the planet essentially ended up becoming cold, dead, and probably lifeless. Okay, so I hope I made the case that really the purpose of missions like the Mars 2020 Perseverance Rover is to understand the processes that made the Earth and potentially other planets suitable for life. And in understanding those processes, we would like to understand why life never developed on other planetary surfaces as well, right? So we can sort of rephrase this in the form of a question. So did life ever emerge on early Mars? And that is really the question that we're after here with the Mars 2020 Perseverance Rover. And along with that, if so, how did it emerge on early Mars? And if it didn't, why didn't it? We live on a planet that's inhabited. Essentially every environment that we can study on the Earth is inhabited by microbial life. And so to discover a planet where environmental conditions may have been habitable, but it was uninhabited, is a very valuable study in planetary environments and their capacity to support life, especially if many of the other ingredients that we think are critical to develop life were in place. And it never got started. That allows us to focus in on reasons why that process might have become frustrated. So the last thing I'll mention in this thread here is, what do we mean when we say life? So when we say life, a lot of us probably think of macroscopic life like plants and animals and humans. But really, when we say life, we're talking about simple microbial life, or what we call prokaryotic life. And it's worth underscoring in this context the significant difference in complexity between prokaryotic life on Earth and eukaryotic life on Earth. The eukaryotic cell, from which we're developed, and plants and animals as well, is the result of billions of years of evolution. Although this image makes it seem like the eukaryotic cell is similar in size to the prokaryotic cell, on average it's much, much larger. But more importantly, the eukaryotic cell contains a whole suite of molecular machines that run specific tasks that produce enormous amounts of energy and really provide a platform for complexity that can never be observed in prokaryotic life. Prokaryotic life, on the other hand, or prokaryotic cells, could simply be described as bags of DNA inside a cellular membrane. And so when we speak about the possibility for life on Mars, we're relatively certain that we're talking about prokaryotic life, or relatively simple life, and that complex eukaryotic life is probably a consequence of our own unique evolutionary history on planet Earth. So where do we go to look for traces of ancient life on Mars? Well, the Perseverance Rover ended up going to a place called Jezero Crater. And as I mentioned, it's too cold and dry for life to exist on Mars today, but Jezero Crater formed billions of years ago, between 3 and 4 billions of years ago. And after it formed, water filled it to form a deep lake about the size of Lake Tahoe in the northwestern US. But eventually Mars's climate changed, the lake dried up, and surface water disappeared from the planet, as I alluded to a few slides ago. And a lake is a great place to go to look for signs of ancient life, because lakes on Earth, we know, are filled with various organisms, and evidence of those organisms ends up getting preserved in sedimentary deposits. So here you can see outlined in blue a river that's carved a channel that essentially deposited sediments in the form of a delta into the lake as the water hit the lake and the sediment load was dropped. The white path illustrates the general path that the Mars rover will take over the course of its mission. Through the mission, we hope to explore the delta deposits and eventually reach what we think are deposits reflecting the ancient shoreline of the lake that resided in Jezero Crater. But even beyond that, an extended phase of the mission we hope will involve investigating the crater rim and the geology associated with that crater rim, which potentially could provide evidence for hydrothermal systems developed in the aftermath of what was essentially a very large impact. So you can see this this white traverse sort of becomes kind of a dashed line, because it's relatively uncertain how that's going to develop. Okay, so a little bit about the Mars 2020 Perseverance Rover mission, in case you're not familiar. The Mars 2020 rover has a number of different cameras that are positioned at various points in the rover, on the top of the camera mast, and also at the end of the arm, which contains a number of fascinating instruments. The rover itself is about the size of a Mini Cooper, which makes it all the more amazing and unbelievable that it landed the way that it did. One of these cameras is called SuperCam, which is actually a laser ablation instrument. So it can actually study targets from a few meters away and obtain some information about their chemical composition. And the MAST-CAM-Z instrument is a set of panoramic cameras that that provides context imaging in exquisite detail and is capable of relatively high zoom. So this is just an artist's conception of how SuperCam actually works. It ends up being a fantastic instrument for collecting chemical data on targets that the rover can't actually easily reach. As I mentioned, the rover also has an arm, which holds a number of instruments, including a tool that can abrade the surfaces of weathered rocks to get to the interiors or the fresh surface. It also has a gas-powered dust removal tool, which after it grinds the surface of the rock, it can actually blast the dust off so it can clean off that surface because as geologists, we're most interested in the nature of the interior surface. Now, also in the end of the arm, as I alluded to, there are two instruments which provide some really important information about the chemistry and the mineralogy of the materials that we're looking at. So one instrument is called Sherlock, which is a micro-focus Raman spectrometer. It actually is capable of measuring the luminescence response of the materials it studies. And on the other side of the arm is an instrument that I'm heavily involved in, which is the Pixel instrument, which is a microfocus X-ray fluorescence spectrometer. And what these instruments are designed to do is to create maps, so chemical maps in the form of pixel and potentially mineralogical maps or something close to it in the form of Sherlock, overlaid on top of each other, where we can use those constraints to really come up with a thin section view of the fresh surfaces of rocks that we study on Mars. And this is really an incredibly important aspect of understanding whether ancient rocks provide evidence for habitable environments and life, because as we understand as geologists, the textural constraints are absolutely crucial in unraveling what is undoubtedly a complex history involving billions of years of geological modification. The last thing to mention, as I alluded to at the beginning of the talk, is that the rover carries a sample caching system on the underside of it, where it can collect and store cores their drill cores about the size of pencil lead, and it can store about 40 of those. And the plan is that those cores are going to be left on the surface of Mars, and another mission is going to land, collect those cores, and load them into a sample ascent vehicle, which will blast off from the surface and orbit around the planet. And then a subsequent mission, an orbiting mission, will rendezvous with that sample container and slingshot around Mars and drop that sample container off into Earth's orbit. So that succession of 3 missions is already in planning and development, and NASA and the European Space Agency, including the UK, are heavily involved in developing these missions, and so they're relatively far along. Okay, so one of the last questions is, what are we looking for, and can the rover really detect traces of life? So to answer that question, it's useful to bring in the term biosignatures. So really what the science team can do with the instrumentation in situ on the surface of Mars is look for something that we consider to be a biosignature. And a biosignature, as I've defined it here, is really any object or substance or pattern that only biological processes that can create. So an example would be an organic molecule that we know is only created by biological processes that could potentially be preserved in ancient sediments. So this is effectively how biomarkers work. It's a crucial aspect of sedimentary geochemistry, and we know that organic molecules can survive billions of years in sedimentary rocks. The Sherlock instrument is potentially capable of detecting organic molecules, but another type of biosignature that might be observable to instruments like Sherlock and Pixel would be, for example, stromatolites. Something that many of us are familiar with, especially those of us that study Precambrian geology. And so stromatolites are basically a manifestation of the interaction between the environment or sediments provided by the environment and microbial mats. And the activities of those microbial mats and the incoming sediments end up modifying the sedimentary deposits in such a way that it can be indicative of the former presence of microbial mats. Now, I'll say that not all stromatolites are indicative of former life. There's actually abiotic processes that can result in morphologies like the ones I'm showing now. But this just gives an example of perhaps an extreme example of a biosignature that we're familiar with on Earth. And so I'll just wrap up the talk now with telling you a little bit about what we've done and what we've found so far and what we're planning to do. So we'll start off with some geology. So this is a USGS map of the Jezero crater landing site. This is a scientific investigation that was launched by a few geologists at JPL. And this product was produced for the USGS, and it's really a fantastic product. I'd encourage you to read the pamphlet that accompanies this and study the map. It's really fascinating. The black dot indicates the landing site, and so we landed a few kilometers away from the delta deposits, which are illustrated in blue. And the first thing that we decided to do is understand the rocks that we're driving over, which correspond to this pink unit called CFFR, or crater floor fractured. Further, we decided to drive up to the first contact that was accessible to us, which is the contact between this orange unit, this NLE unit, and the CFFR unit. This orange unit is thought to be in place after the lake deposits were, well, I think that unit was deposited during or after the deltaic deposits were in place. It's difficult to distinguish between the two possibilities. But nevertheless, that was an important geological target for us. So this is a higher resolution view of that area. So you can see this yellow dashed line illustrating the future traverse that we're going to take. We ended up moving from the Octavia E. Butler landing site south to explore a region that we dubbed CETA. And around the very southernmost expression of that yellow dashed line, ended up studying a few rocks basically along that contact between the crater floor fractured unit and this unit that looks like it's been embayed into the CFFR unit. So we attempted to abrade two patches on the rocks to expose fresh surfaces, and this is all part of a sequence through which we collect cores. So the way we collect cores is that we study the surface of the rock in a place adjacent to where we ultimately collect the core, and we assume that the location we're studying the abraded patch on is representative of what's in the core. So this is just an image of one of the abraded patches and our subsequent coring activity to sample that rock. Some of you may be familiar with the first attempt by the Perseverance Rover to sample a core. It actually turned out to be not so successful. So this is an image of the sample tube showing that it is in fact empty after the sequence ran, and we expected the core to be in it. This sort of set off alarm bells in the JPL NASA flow of things, and there were teams of people devoted to understand what could have possibly have gone wrong. But it didn't take long until a few of the science team members studied the imagery and came up with a much simpler observation that ended up being validated by the engineers, which was that the core was obliterated during the coring process. So this is an image of the core taken during the night. And you can see that basically what's left in the core and around the core is a huge amount of fine-grained debris. So that was highly frustrating to project management at JPL, but of course the geologists were fascinated. So what is it about this rock that means that it's so incoherent? And we wanted to understand more about the composition and what it was telling us about geological processes at Jezero crater. So what I'll share with you now is some of the detailed data that we collected from the Pixel instrument. And I'll talk a little bit about the Sherlock instrument, but what we did is study those abraded patches. So there are two locations where we've done this and collected Pixel scans and Sherlock scans to understand the geochemistry and mineralogy, to basically ask the question, what's going on with this rock? And so I'll give you some of the first examples of chemical maps ever collected on a fresh rock surface on Mars. So this is an iron aluminum chlorine map of that fresh abraded surface that I just showed you. And you can see right away that there are some regions that are dominated by very high total iron concentrations, up to about 60 weight percent. There's of course aluminum rich regions, which end up corresponding to plagioclase. And you'll notice that there are high concentrations of chloride in this material as well. In the same location, I'll show you a sodium sulfur chlorine map. And you can see that, that there are pink pixels because the sodium is in red, the chlorine is in blue. And so when they mix together, you end up with this purple pink color. And so we think that's a good evidence that we've got halite. And so it turns out that the sodium and chlorine actually vary sympathetically in a 1-to-1 stoichiometric ratio. So in addition to halite, there's also a number of sulfate minerals, including gypsum and some magnesium sulfate. So altogether, we've got evidence for clinopyroxene, plagioclase, iron titanium oxides, but calcium sulfate, halite, and this unusual, very high iron and high silica material. And this is something that I and a couple of colleagues have been studying and sinking our teeth into. And this stuff turns out to be really interesting. So if you look at the chemical composition of the most iron-rich material, it turns out that it's very rich in silica as well. And so I've got some of those data points plotted on a ternary here, a magnesium silica iron ternary. And you can see that those blue points from the pixel map correspond to a region in compositional space that's occupied by iron-rich serpentines and also phaolite. In fact, you can see two different mixing relationships that look like some of the minerals, so hissingerite or just generally iron-rich serpentine, because there's evidence that there's a continuous solid solution between hissingerite and greenolite, which are the ferric and ferrous iron serpentines respectively. So it looks like there's evidence for those phases mixing with something that has a composition closer to Cronstedt type. But there's another limb on this mixing relationship that looks like it's being pulled down right to near end member phaolite. And it actually turns out that that material has exceptionally high manganese, and it's distributed in such a way that it appears genetically related to some of the iron-rich serpentines. So this is really exciting stuff if you're a mineralogist, because it doesn't take long to realize that these phases can all be formed in one chemical system that often is generated through serpentinization of ferro and olivine. So there are a number of fantastic examples on the Earth where this process takes place. The Duluth complex in Minnesota, the Laramie complex, and the Overlook gold deposit in Washington, for example, where you've got complex intrusive processes that end up forming iron-rich protoliths and iron-rich olivine, and that iron-rich olivine is hydrothermally altered. And when you alter hydrothermally alter iron-rich olivine, you end up generating a suite of iron-rich serpentines and potentially phaolite. So there's evidence that phaolite can actually be stable down to about 150 or 200 degrees C. But because we've got evidence for it here, it could potentially provide us with a key constraint on redox and a minimum constraint on temperature associated with hydrothermal alteration that we think is generating this suite of iron serpentines. So our working hypothesis, and please, I ask you not to post this on social media because it was too exciting not to share some of this with you, is that we're entertaining scenarios where emplacement of gabbro in or next to the crater floor rocks might have set in motion a convection cell or otherwise triggered serpentinization of ferro and olivine, which then generated iron silicates and potentially remobilized or were associated with precipitation of saline minerals. It's possible the saline minerals could have been precipitated later, but there's some close textural relationships that suggest that they potentially formed from the same fluid. We haven't quite nailed that down yet. But the fact that we can speak about such processes in detail about the geology in another planet is really striking. So I'll just conclude here with one more thought. I guess the one thing to say is we've already sampled these materials, so we'd better be right about this interpretation, because these cores are actually coming back to Earth in 10 years. But the last thought I'll leave with is the question, what does this end up telling us about planetary environments and the origins of life? The evidence I've just described from the crater floor fractured rocks from our study of those targets essentially indicates an environment where we might have the emplacement of a gabbro around the same time as salt mineral precipitation that could have been driven from the Jezero crater lake. This is a working hypothesis, but there are tests that we can apply to this hypothesis as the rover moves forward. But this is a scenario very similar to the scenario that I just described that's come out of a lot of this work focusing on prebiotic chemistry. And this is a really exciting sort of scenario to entertain, because it suggests that this sort of a scenario might actually be feasible, and there may have been environments where prebiotic chemistry could potentially have been facilitated. And so if all these ingredients were in place and nothing happened, or there's no evidence for life, then that gives us a starting point to ask why Mars is potentially so different than the Earth, or at least why early Mars is potentially so different than the Earth. So I'll just leave it there, and thank you very much for your time, and I'm more than happy to take any questions.
Thanks very much, Nick. We've overrun a bit on that, so I think there aren't any questions in the Q&A for the time being. So I think we'll leave the questions for people to ask you personally if they can come over to the Gather Town. So I'm just going to hand over straight away to Rich just to wrap the session up. Rich.
Thanks, Nigel. And yeah, I just want to say a huge thanks to both speakers. They're fantastic talks. And what strikes me whenever I see the sort of images that the rovers produce is just how important the sort of observations that Marion was talking about are. Those sort of field scale observations that you can do in the field that look at the processes. Those are the same skills that you need to interpret some of the images that come off these rovers. And I think that's an important message we often give to our students in the field, that the sort of skills that we're giving them are not only useful for looking at the rocks down the road, but for looking at planets across the solar system. And so thank you both for those fantastic talks. So what I'd hope to encourage everyone to do now is to head over to Gather Town, and you'll have a chance to ask questions to Nick and Marion there. To do that, there is a link in the chat. So if you go to the chat function there, click on the Gather Town link. That should take you to Gather Town. If you just enter your full name there, choose an avatar, and then enter the Gather Town environment, you'll be able to roam around and bump into people and have a chat and go and seek out our speakers, or Nigel, or me, or anyone else who's around there. So I'll wrap up now and thank our speakers again. And yeah, if you now click on the Gather Town link, either in the chat or in the email that the alumni team would have sent you before the seminar, and we'll hope to see you there. Thank you.